The topic of my talk is on some applications of measures of non-compactness. So first, we will describe the basics about the sequence spaces, matrix transformations, and measures of non-compactness, and their application to find the compact matrix operators and to solve infinite system of differential and integral equations. This is my book with Professor Banach, a Polish well-known mathematician. Here we have also covered all these topics. It was published by Springer. So let me start some basic definitions and notations. We denote by X the nonlinear space and Sx and B bar X as the unit sphere and closed unit ball in X. By Bxy, we denote the set of all bounded linear operators L from X to Y. A linear operator L X to Y is said to be compact if the domain of L is all of X, and for every bounded sequence Xn in X, the transformed sequence has a subsequence which converges in Y. Then we call this as the compact operator. And we denote the set of all compact operators by Cxy. So here we see that we study some matrix transformation between sequence spaces, and then we achieve the compactness through measures of non-compactness. By small w, we shall denote the space of all real or complex sequences, and this phi denotes the set of all finite sequences. Finite sequences, we mean that those sequences which have a finite number of non-zero terms. The rest are zeros. By E and Ek denote the sequence of ones. Ek is the sequence whose non-zero term only is 1 at kth place. These are the classical well-known sequence spaces, LFTC and C0, sequence space of bounded sequences, convergent sequences, and null sequences or sequences converging to 0. And L1 and LP are also well-known classical sequence spaces of all absolutely and p absolutely convergent series respectively. Furthermore, we write BS, CS, and C0 as the series version of these spaces, that is bounded series, convergent series, and the series converging to 0. So here, besides the continuous dual, there are several other duals of the spaces like alpha dual, beta dual, and gamma dual. These are defined as this X, that the alpha dual of X is this one, where the product sequence belongs to L1. L1 we have already mentioned the notation, and the beta dual of X is defined as this, that the product sequence is a convergent series for all X belonging to X, similarly for bounded series. So these are the definitions of alpha, beta, gamma duals, especially this middle one. The beta dual is very useful in characterizing the matrix transformations from one sequence space to another sequence space. Here we define the matrix transformation. Let A equal to A and K belongs to N, be an infinite matrix with complex entries. That is, all the rows and columns both are infinite. Then we write An for the sequence in nth row, that is, An is this sequence. And for if X belongs to W, then we define A transform of X as the sequence Ax equal to Anx, where Anx is this much. That is the A transform of X, and provided this series converges for each n. Then we define the A transform of X. Let X and Y be subsets of W. These are two sequence spaces, and A be an infinite matrix. Then we say that A defines a matrix transformation from X into Y, and we write like this: if AX exists and belongs to Y for all X belonging to X. So it means that for any matrix A and Xy any two sequence spaces, if A transform belongs to Y for all X belong to X, then we say that A defines a matrix transformation from X into Y. And by xy, by this pair xy, we denote the class of all infinite matrices that map x into y. Thus A belongs to xy if and only if this, here we use the beta dual of x. So this definition can also be given in this way. That is, A is a matrix transformation from x into y if this AN, this sequence AN belongs to x beta. That is beta dual of x, and AX belongs to Y for all X belonging to X. Then we say that A is a matrix transformation from X into Y. Here, besides these simple sequence spaces, there is also a related theory that is known as FK space theory. That is, a sequence X is called an FK space if it is complete linear matrix space with continuous coordinates. Continuous coordinate means this map is a continuous map. That is Pn from X to Y. X is any sequence space. C is the set of all complex numbers. So this is defined by Pnx equal to Xn. That is the nth coordinate of the sequence for all X belonging to X. If this map is continuous and X is a complete linear metric space, then this sequence space X is called FK space. And if this space has NOR, if it is non-base space, then we call this as a BK space. A BK space is a norm FK space. That is, BK space is a Banach sequence space with continuous coordinates. The classical sequence spaces are BK spaces with their natural norms. More precisely, these are the examples of BK spaces with subnorm, the usual norm. Also, the space is a BK space for this value of P. For P equal to infinity, it is not. Here we define the shorter basis for our spaces. This idea is also an extension of Hamel basis. Hamel basis, we deal with finite dimension. Now, for infinite dimension, we define the basis as shorter basis. A sequence Bn in a norm linear space X is called a shorter basis for X if for every X in X there is a unique sequence of scalars such that that every element of X can be expressed as the infinite, or this also can be written like this. These spaces C0, C and LP for the value P for this have all shorter bases, but the space L infinity has no shorter bases. Okay. An FK space is said to have the property AK, or an FK space is called the AK space if every X belong to X has a unique representation like this. It means that if an FK space has a shorter basis, this sequence EK, then we call that FK space as AK space. C0 and LP have AK space, while N entity has no AK space because its Schroeder basis is not that sequence. And we write for some particular norm like this. If X contains phi, is a PK space and A belongs to W, A is any sequence, then we define the star norm by this, provided that the expression on the right hand side exists and is finite, which is the case whenever A belongs to X beta. This is same as A belongs to X beta. And these are the basic results about the alpha, beta, gamma duals of these classical sequence spaces. Also, the relation between the norm, usual norm, and the star norm is this. And this lemma 1.3 is very important lemma. That X be containing X contain phi and Y be BK space, then the pair XY is subset of BXY. It means that every matrix A belong to XY defines an operator, bounded linear operator. That is, every matrix transformation defines a bounded linear operator, and that is given by this relation. So it means that every matrix transformation defines a bounded linear operator. And the converse of this lemma is also true if X has AK space. If X is AK space, then the converse of this lemma is also true. That is, for every bounded linear operators, there correspond a matrix transformation. But for this is the condition that X must be AK space. So here is the point that every matrix transformation can be represented by a bounded linear operator. By this, what about the compactness? Because this ensures that it is bounded linear operator. But what about the compactness? And that compactness can be achieved by using the Hausdorff measure of non-compactness. That is why here we apply the measures of non-compactness to achieve the compactness for these bounded linear operators. So here we give a brief introduction of Hausdorff measure of non-compactness. There are several other measure of non-compactness, especially this Kurtowski measure of non-compactness was the first one. And this Hausdorff measure of non-compactness has some application here in achieving the compactness of the bounded linear operator. This is defined by this. By Mx, we denote the collection of all bounded subsets of a metric space Xd. If Q is any bounded subset of a metric space X, then the Hausdorff measure of non-compactness of this Q, denoted by chi Q, is defined by this. The function chi is from Mx to this interval is called the Hausdorff measure of non-compactness. It means that what is the idea here? That is, this bounded subset of a metric space X, how this can be covered by a finite number of balls with center xi and radii ri less than epsilon. So this is the definition of Hausdorff measure of non-compactness of a bounded subset of a metric space. Here are some properties. If Q1, Q1, Q2 are bounded subsets of a metric space Xp, then we have these properties. And further, if X is a non-metric space, here it is, X is metric space. If X is non-metric space, then in addition we have these two properties, which are of course inherited by the norm space. Yeah, this is repeating about the shorter basis. So here are some important theorems. Sorry. How to calculate the Hausdorff measure of non-compactness. Let X be a Banach space with shorter basis Bk. Q is a bounded subset in X, and Pn X to X be the projector onto the linear span of this. Then we have this formula. So through this formula, we can calculate the Hausdorff measure of non-compactness for any bounded subset of a Banach space X. And this is very useful formula, where A is this and I is the identity map and Pn is the projection from X to X. For example, here, if we take X as the space LP or C0, then through previous formula, we have the Hausdorff measure of non-compactness for these two spaces LP and C0 is given by this. So through this, we can easily obtain the Hausdorff measure of non-compactness for any bounded subset of the spaces LP and C0. In particular, we have this. That is after calculating this part. After calculating this part, we get this for LP space for C0. And for other spaces also we have for C and for function spaces and so on. Here is the relation. Let Q be bounded subset of the normed space X equal to C. C is the space of convergence sequences. Since this is the shorter basis for C, we have this estimate where mu Q is any measure of non-compactness for the space C. Here is one more thing that we define the in previous slides we have defined the Hausdorff measure of non-compactness for a bounded subset of a metric space or nonlinear space. Here we define the Hausdorff norm for any bounded linear operator from X into Y. Then the Hausdorff measure of non-compactness of L, denoted by this. Also we call this Hausdorff norm by this. That's the Hausdorff measure of non-compactness for this transform unit sphere, which is same as this. And further we have that L is compact if and only if this norm is 0. And here we come to the application of these Hausdorff measure of non-compactness. That is, we have already denoted how to calculate the Hausdorff measure of non-compactness for these species and how to define the norm for these operators. Then here we come to our aim to achieve the compactness for these operators. The general method for the characterizing of compact operators between BK species, simply we say sequence species, and can applied whenever Y has shorter basis. First step is that determine the beta dual of X, not necessarily for Y, then characterize the class this, or even sometimes we have already characterized classes, then compute the operator norm as given by the previous formula, or find an estimate for the operator norm of the matrix operator from X into Y. Use the Hausdorff measure of non-compactness to find necessary and sufficient conditions on the entries of the matrix to be compact operator between X and Y. This method cannot be applied in general in case when the final space by this space y has no shorter basis, then it only yields one-way condition, sufficient condition only. But if it has shorter basis, then we have if and only if condition. Here are some known classes. These are very popular and known classical matrix classes. And if L is a bounded linear operator from L1 to L1, where A is infinite matrix such that Lx equal to Ex, this is already from our previous result that for every bounded linear operator, because these spaces have AK space, so we can associate with this bounded linear operator a matrix transformation from X L1 to L1. So this Lx can be defined by a matrix transformation Ex. Then we have this Hausdorff norm of L by this. From our previous results, we calculate this one, and for this class, we have this. So as in our previous result, we stated that L is compact if and only if this norm is 0. So this norm is 0, it means this amount is 0. Then L will be compact. So in the next, we have this one. So L is compact linear operator from L1 to L1. If and only if we have this. Similarly, for this class, we have L is compact if and only if this condition holds. So you can see that how the compactness can be achieved. We already have some association of matrix transformation with a bounded linear operator. So then that bounded linear operator may be compact if we can apply the Hausdorff measure of non-compactness in this way and calculate the Hausdorff norm, and making that norm equal to 0, then we get the condition for L to be compact. It is not true that every operator is compact. So it is obvious, but we have given here an example also. For example, let I be an identity operator from L1 to L1. Of course, it is bounded linear operator. Then it is obvious that L cannot be a compact. Why? Because when we calculate this Hausdorff measure of non-compactness for this, which comes 1. Hence, it follows that norm of I equal to, as from the definition of the Hausdorff norm, we have this. So this is equal to 1. So which is not 0. This is not 0, it means that this I is not compact. So here are some other results about the compactness for matrix transformations using different classes. Here X is any BK space. Then we have A belongs to X to C0. If this belongs to A to X0, then we have this. If X has a K space or X equal to L infinity and A belongs to X to C, then we have this. So all these are derived through our previous formula. If A belongs to X to infinity, then we have this in one-way condition. So these, once this norm is calculated, we can achieve the compactness. Thus, just making this equal to 0, then the condition will be obtained. And let us remark that the limit 3.4, 3.5, and 3.6 exist by lemma 1. Here, these limits all exist by our previous result. And A belongs to Xc, then the sequence of non-negative reals is non-increasing and bounded by lemma 1. So we demonstrate here the proof of, there is no, we don't demonstrate here the proof, just we skip the proof here. Then as corollary, so from that previous, this theorem, we have calculated this, and so this operator will be compact if this norm is 0. This norm is 0 means this thing is 0. Similarly, here this is 0, then this LA will be compact if this is 0. Okay. Similarly here. So here we get this. And as a corollary, we achieve this compactness about the bounded linear operator. And there is again one more result where it shows that for this class we have only one way condition, not if and only. But in the previous these two we have if and only, but in this case we have only one way condition, and this is shown how it is one way. The other way is not true. Similarly, if we get the second space as L1 space, then we have this inequality, and this is LA will be compact if this is 0. If this is 0 means this amount of limit is 0. So here we add the application of Hausdorff measure of non-compactness in characterizing the compact operators. Here we come to our application of these measures of non-compactness in differential equation, especially in the infinite system of differential equations. And we consider, because we have infinite system of differential equations, so collectively we will have a solution of this system as a sequence, because this is infinite system. So we will have the solution as a sequence, and we have to study what is the nature of that sequence of solutions. That means that sequence which we obtain as a solution of the infinite system of differential equation belongs to certain class of these spaces like C0, C, L, P, and other also. So here we have given to find the conditions how this system of differential equation will have a solution, and that solution, that sequence of solution belong to which class. And there are also, beside the sequence spaces, there are also these about the differential solution of differential equations have been studied in function spaces also. Several authors have considered some function spaces too. So these are the basics about the. So here comes another type of measure of non-compactness. In fact, this is not another type. This is the axiomatic definition of measure of non-compactness, which covers all the previously defined measures of non-compactness. And this definition was given first by a Polish mathematician Joseph Banach, who is also co-author with me in the book. And he gave this definition. And this definition is very handy and useful and easy to apply. So this definition covers all the measures of non-compactness defined previously. For example, Kurzowski measure of non-compactness, Hausdorff measure of non-compactness, and there was one more, Stratowski measure of non-compactness. So the function mu from AMI. AMI is the set of all. This is the set of all bounded sets in E, where E is the metric space, and if it is one non-linear space, then it will have some more conditions. If these conditions are satisfied, then we have this function defines a measure of non-compactness, general measure of non-compactness. Let mu be a measure of non-compactness in Banach space. We call the measure mu to be homogeneous if this satisfies this. And these are in fact the conditions by through the Banach space, subadditivity and homogeneity. We say that a measure of non-compactness mu has the maximum property if this holds. Finally, let us provide the definition of a classical measure of non-compactness, which is closely related to earlier discussed Krotowski, Hausdorff, and Stratowski measure of non-compactness. A sublinear measure of non-compactness mu, which has the maximum property and is such that kernel of mu equal to any is called the any is the family of non-empty and relatively compact subsets of E. And we have this inequality. This is also very important inequality because through this we calculate the measure of non-compactness for any bounded subset X of a Banach space. Here we come to our main concern. In this section, we adopt the technique of measure of non-compactness to the theory of infinite systems of differential equations. Particularly, we are going to present a few existence results for infinite systems of differential equations formulated with the help of convenient and handy conditions. So first we give about this set of differential equation. Consider the ordinary differential equation this with initial condition this. Then the following result for the existence of Cauchy problem. Sorry, this is 4.1, 4.2, not 5.1. So please. Was given in 9, which is a slight modification of the result proved in 3. What are the results in 3? I will state later on. So assume that X is a real Banach space with the norm this. Let us take the interval I is equal to 0 t. T is any positive number and Px0 as the standard notation for closed ball in X centered at 0 and radius r here. Assume that f dx is a function defined on I cross x with the values in x such that this holds for any x in x where q and r are non-negative constants for the let f be uniformly continuous on the set this, where r is this and I1 is this. Moreover, assume that for any non-empty set y in Bx0 R and for almost Rt in I, the following inequality holds with a sublinear measure of non-compactness mu such that x0 belongs to kernel mu. Then the problem 3.1, 3.2 has a solution x such that xt belongs to this kernel. Again, here is some typos. This is 4.1, 4.2. This system. Then this system has a solution such that xt belongs to kernel or t belongs to L1. Now, this is for a system ordinary differential equation, this one. Now we come to our infinite system. Here we have this already we have given. Here we consider the infinite system of differential equation. So this is an extension of the problem, Cauchy problem 4.1, 4.2. Here we take xi dash equal to this one with the initial condition this, which are defined on the interval I and such that xt belongs to C for each t belongs to I. Then we assume these conditions. Assume that the function fi are defined on the set I class R infinity and take real values. Moreover, we assume the following hypothesis, that is x0 belongs to C0, the map X from I cross C0 into C0 and is continuous. There exists an increasing sequence Kn of natural numbers. Obviously, Kn tends to infinity as n tends to infinity, such that for any t in this, X belongs to C0 and n equal to this, the following inequality holds. This holds where PIT and QIT are real functions defined on the continuous and are continuous on I, such that the sequence PIT converges uniformly on I to the function vanishing identically, and the sequence QIT is equibounded. So these are actually some conditions we have to assume for the existence of the solution of infinite system of differential equations. And so under these assumptions, what we have finally, this one, under the assumptions above 1 to 3, initial value problem 4.4 to 4.5 has at least one solution, x equal to xt. What is xt? Xt is the sequence of solution xit defined on this interval, and qt1 is less than 1. Moreover, this solution, this sequence of solutions belongs to C0. So far as sequence of solutions belonging to this space, we have to assume these three conditions, including this one. So here is our main concern, that how we achieve our aim, that is the existence of the infinite system of differential equations is achieved by applying the measure of non-compactness, and after that, how that system of equation, that solution, that equation, that sequence of solutions belong to certain sequence space. So accordingly, we have to change these conditions. Okay, here we have assumed these three conditions, and these are the notations, and this qt1 is less than 1. So under these three conditions plus this condition, we have that this sequence of solution belongs to C0. Similarly, what will be these conditions or these assumptions if we change this space? In our next result, we have changed this space as the LP space. Here we consider the same system of infinite differential equations with initial condition 4.5, how that sequence of solution belonging to this space LP. Here, instead of three conditions, we assume two more conditions. So under these five conditions, under these conditions, we have that sequence of solutions belong to LP space. So this is what we do here. This system, this actually here, this one, sorry, this theorem ensures the existence of this solution. But our next step is that because we are considering the infinite system, so we will have a sequence of solutions, and that sequence of solutions, we have to study the nature of that sequence of solutions. That is, that sequence of solution may be unbounded, they may be bounded, may be convergent, may be belonging to the space LP, belonging to the space C0, and so on. because it is a sequence, so it must having some properties of that must belong to certain class of sequence spaces. So here for the space LP, and there were many other papers just changing this space or changing the set of infinite system of differential equations, sometimes first order, second order, third order, and so on. So there were many papers published on this topic, especially on infinite system of differential equations belonging to different classes of sequence spaces. Next, our application is shown here for integral equations. So just to apply the theory of measures of non-compactness to integral equations, we describe the Darboux theorem and its generalization. Then that theorem is used to find the existence of the solution of integral equations as well as system of integral equations, infinite system of integral equations. Darboux formulated his celebrated fixed point theorem in 1955 for the case of Kuratowski measure of non-compactness. This was the first theorem which involves the notion of measure of non-compactness. And this famous theorem of Darboux also generalized the Schroeder fixed point theorem. Quite recently, an extension of Darboux's fixed point theorem has been given in this and use it to study the problem of existence of solution of general system of nonlinear integral equation. Here is the Darboux's fixed point theorem. Let E be a Banach space, M be a subset of E, non-empty, closed, convex, boundary subset, and T be a map from M to M, a mu condensing operator, this equal to K, norm of T is K less than 1, then actually this operator we have already given how to calculate the norm of the operator. Okay, then this operator is said to be condensing if norm of this is equal to K less than strictly 1. That T has at least one fixed point and the set of fixed points of T belongs to kernel of mu, where mu is an arbitrary measure of non-compactness. Mu is any measure of non-compactness. That is why for this use we have made the axiomatic definition of measure of non-compactness. It may be any measure, but Darboux used first time Darboux used the Kuratowski measure of non-compactness. Here in 1969, Nier and Keeler proved the following very important fixed point theorem, which is generalization of Banach contraction principle. So first they defined the Meyer-Keeler contraction by this. Let X be a metric space, then a map T on X is said to be Meyer-Keeler contraction if for any epsilon greater than 0, their X is delta greater than 0, such that this inequality holds, this relation holds for all xy belonging to X. And this was the theorem given by Meyer and Keeler, and this generalized the Banach contraction principle. X may be a metric space. If T is a Meyer-Keeler contraction, then T has a unique fixed point. And this, both this definition and this result was generalized for measure of non-compactness. Here, let C be a non-empty subset of a Banach space E and mu be any arbitrary measure of non-compactness. We say that an operator T is a Meyer-Keeler condensing operator. That is, we use the word condensing by using the measure of non-compactness if this condition holds. And this is the generalization of the Meyer-Keeler contraction principle. Yes, so there are some more notations which are used in our theory of solving the infinite system of integral equation, or any, not necessarily infinite, but any system of integral equations. Let C be a non-empty, bounded, closed, and convex subset of Banach space. T be a continuous operator for each n where mu is arbitrary. Then T has a fixed point. This is in fact the Darboux fixed point. This is the theorem we have generalized from the Mere-Keeler contraction principle. Note that if theta is kt, where k is this constant, gives the Darboux fixed point theorem. So this theorem is a more general case of Darboux fixed point theorem. For this special case, it is reduced to Darboux fixed point theorem. Here we consider this hypothesis. Let BC R plus cross R plus be the Banach space of all bounded and continuous functions on R plus cross R plus equal with the standard norm this for any non-empty bounded subset X of BC. X belongs to X, L greater than 0, L epsilon greater than 0, that WLXE denote this, and all these we make the notations, and mu1x equal to this. Then assume, now we get this result from these notations. Assume that the following conditions are satisfied. Just like in the case of differential equation, we have certain assumptions on this function, these two functions, and m be supremum of this less than infinity, and this g is continuous and there exists a positive constant d such that this d is equal to supremum of this integral, and moreover we have this limit uniformly with respect to xy belongs to b, bc, r cross r plus cross r plus r. There exists a positive solution r0 of the inequality this. Then the functional integral equation. This integral equation has at least one solution in the space BC R plus cross R plus. This is actually two-dimensional integral equation, and that this type of integral equation will have a solution under these assumptions. So here we see that another application of measure of non-compactness, which are given for the integral equation. And there also there are many results on these integral equation as well as infinite system of differential equations. Again, that those solutions of the integral equations belong to certain sequence space and so on. And also some higher order differential equation can also be converted into integral equation through Green's function, and then solving those integral equation equivalently give the solution of the corresponding differential equation. And that again we study that solution, the nature of the solution. So here are certain very important references. And this is the first book by Banach and Cowell, where they discussed several measures of non-compactness, and also in this book they give the axiomatic definition of the measure of non-compactness. And Banach and me also wrote recently in 2014 that book, and it covers more topics related to sequence spaces, their topological properties, and their um, connection with matrix transformation, then compact operators, then their application to differential and integral equations. So there are several. And recently, in 2016, I have one paper with my student, PhD student, which was published in Proceedings American Math Society. And here in this paper, we considered the second order differential equation, infinite system of second order differential equation, and studying those second order differential equations C0 and L1. And later on, there were several other papers by different authors who considered these spaces LP space or other spaces, so on. So there are several other sequence spaces also which can be considered or which can be replaced here. And this second order can also be replaced by higher order and so on. So that's it. Thank you very much.